Yes.
We don't have a class, no?
We should have a class, but
Nobody's up here?
I don't see anyone.
I just missed the bus.
No one here. I'm waiting. Class. One. Here.
No,
It's
we
a
don't.
cone.
We have it, right?
Yeah. No one. No one. No one arrived. Okay. It's their problem. No, wait 2 more minutes. Friday. Parking lot was also empty. No one wants to work on Fridays. People. I have signal is very nice signal. Wait for someone to understand it.
You're recording the video?
I'll start. Now it's only. Now it translates only coming soon.
You have a YouTube channel?
Yeah.
What was the name for the channel?
Check your e-learning system. It's my surname, but check your e-learning system. It should appear. You have this course in your e-learning system.
Yeah, but I couldn't have attended for the previous classes. It's my first private one.
Not a giant problem because recordings are available. That's why I do recording. You see?
Yeah.
Recording for previous year and this year. Okay, let's do something. What my plan for today is a resonant circuit. It was starting. We are interested in a resonant circuit. On the one hand, they are often used as bandpass filters, and on the other hand, we are often interested in resonant over voltages to keep them under control. Okay, let's start. Say I have a network of AC source, coil, resistance, and capacitance. some kind of S0, maybe even function of time, and here should flow current also as a function of time. Can I write Kirchhoff's voltage law for this circuit?
Kilos of voltage?
Yeah, voltage law for this circuit.
Yeah.
Why not? So it will be Ri plus A I first derivative of current, this voltage, plus 1 divided by capacitance time A time equals to E0 as a function of time. Is it correct?
I believe so.
Appears. In front of me is a differential equation. I need to solve it. First, I need to be transformed. Perform a small transformation on it. No, I was wrong. Everything fine. So, what can I do with this? I need to take a derivative and or multiply by capacitance or divide by inductance. I prefer division. I'll divide by L. So I will have second derivative of current plus divided by L first derivative of current plus 1 divided by LC my current equals to first derivative of my voltage. Now, key moment. To analyze transients or circuits in dynamics, I need to separate free and enforced or stable regime. No idea of transients. Two modes or two regimes. So what is enforced regime? Okay. On the base of very simple example. Let's say I have simple math resistance, let's say 1, capacitance, this is ground, this is ground, maybe like this, R2, switches at time 0, and here is my voltage as a function of time. Time, voltage is a function of time. Here is 0. What will be voltage before the 0 time? switch is turned.
So the switch is on now?
Switch now, let's start from a moment when switch is off. It goes on at time 0. Now, before 0, what will be voltage?
Is it 0?
You should return to basics of electrotechnics. What's the resistance of capacitor? Ideal. From electrotechnics theory. Infinite. What's current here? 0. What current here? I have DC source. 0. Voltage flow on R1 is 0. So voltage here equals to EMF. Yes? Next question. In infinite time, what will be voltage?
0.
No, you're not fit for this course.
I'm not?
No, not. You don't know the basics of electrotechnics. You don't know basics of electrotechnics. You should again undergo course basics of electrotechnic theory. You mark at this moment. How can it be 0? Time infinite. Switch is on.
Okay. So it's going to be infinite? Or like equal time?
No. Again, you need to return to basics of electrotechnics theory. For the capacitor is fully charged. Current to capacitor is 0. Current flows only through this resistor. Current will be E divided by R1 plus R2.
Yeah.
Voltage drop on this resistor will be current multiplied by R2.
Okay.
So, this line is E R2 divided by R1 plus R2. I can paint it green. Here, green line is infinite time. And between them, orange line. This one falls, it's a capacitor discharge from E to ER2 divided by 1 plus R2. All of this, E power minus alpha time, alpha here, 1 R2 C, and here should be written it's E R2 L1 plus R2 plus A minus I need space. Okay, it's delta. Delta of this, yes, delta multiplied by. It's not to write small letters. So, why I'm drawing this? Red is pre-fold or pre-computation. This one, which corresponds to infinite time, is stable or enforced. and orange is a free component. When we start to deal with dynamic, circuit dynamic, we will seriously simplify analysis if we separate real voltage or real current, real transient in modes, free components and enforced components. Enforced or infinite time or stable component is for time infinite. So when transient is ended, and free components is between previous precomputation and enforced. Now, for my circuit, I need free component first. To get free component, I need to solve a differential equation. Second derivative of my current plus double alpha. First derivative of my current plus omega 0 squared my current equals to 0. Here designation. Alpha is decay factor. It will be R divided by double inductance. Frequency omega 0 1 divided by square root of LC. If you open electrotechnics basics, you will find a current resonance. It's simplified there, but for circuit of coil and capacitance, imaginary part of input conductance equals to 0 when capacitance is fully compensates inductance. This corresponds to frequency 1 divided by square root of LC. Resonance frequency. Okay, what I can do with this equation?
You can go through the free component.
It is equation to obtain free component. Good news, what such kind of equation already solved. It's an oscillation equation. Such kind of equations, so-called uniform equations, are solved. They are solved for different matter, but solution is null. So, solution my free component as time, as function of time, will be I1 a power lambda 1 time plus I2 a power lambda 2 time. Here, I1 and I2 are constants. Constants determine border condition or condition at a moment of computation. In easy word, I1 and I2 are T equals 0, zero time, are determined by zero time conditions. These two are roots of spatial equation.
These are constant values?
Nope. They do not change, but they are determined as a root of equation. They are giving us, how to say, time characteristic of process. What happens? I need to solve equation lambda square 2 alpha lambda plus omega 0 square equals to 0. Actually, there should be a pause. So I will get two roots plus minus square root of alpha square minus omega 0 square. I will get two roots. And it's important. These roots can be or real or complex conjugated. Now, I can simplify recording. I will introduce bet as a square root of alpha square minus omega 0 square. Yeah. Equals to square root of r square divided by 4a square minus 1 divided by LC. Yeah. Now, free current can be written as it's a free as current as a function of time. F power decay I1 F power beta time plus I2 F power minus beta time. Full current contains of two components, free component plus infinite time and forced component. This is enforced component. Let's take simple schematics. Easier to understand. Oh, let's say I have E0 capacitor and a switch at T0. We will see free current flowing
backwards.
It depends on designation. Let it be. For this network, first we need to understand what? Grounding. Border condition. What happens at the moment when switch is turned? Foundation basic of this universe is what? Energy conservation law. Energy do not disappear nowhere and do not come from nowhere.
Flows.
Energy flows, but at the point T0, capacitor charge cannot change.
Yeah.
That's mean what at time 0 and coil current also cannot be changed instantly. So at the time 0, we can say what current is 0 because coil current cannot change. And equals to minus E. Because our capacitor is charged to the voltage of E0.
Yeah.
We got border conditions.
What if we don't have any resistor?
It's not possible. You cannot make coil without resistance.
No, I mean, what if we don't have it in the circuit at all?
Again, impossible to create coil without internal resistance.
Huh, okay.
So there will always be a resistance. In theory, if you have magic coil without resistance and no resistance in circuit, you will get singular network. You will get infinity at the moment. Okay. Do we know now border conditions? Yes, easy. So I2 will be equal to minus I1 and equal to E0 divided by 2 beta L. That's what we... Now we have border conditions. So our free current will be minus E0 divided by double beta L a power alpha time a power beta time minus a power minus beta time. We have free current. What about voltage? What about voltage? Coil voltage, F means free, as a function of time, will be at DEF time equals E0 divided by double beta at power alpha time multiplied by large bracket alpha minus beta f power beta time minus alpha plus beta f power beta time. is free voltage of my coil. Can I write free voltage, free component of capacitor? I can. Free component of capacitor voltage will be minus ULF plus LEF this equals to S0 divided by double beta F power alpha multiplied by alpha plus beta F power beta and minus alpha minus beta F power minus beta step. Okay, free component of my capacitor voltage. Now let's try to go into analysis. There is interesting thing with the root of equation. We can see two different situations. In one case, alpha is less than omega 0. In other case, alpha can be greater than omega 0. Yeah?
Yeah.
Or active resistance is less than double wave resistance. Wave resistance is a square root of divided by C. So if active resistance is less than double wave resistance, beta square root of alpha square omega 0 square will be imaginary. And it will be J omega F, frequency of free oscillation.
Now,
Frequency of free oscillation is omega 0, theoretical resonance frequency, 1 minus x squared divided by 4 rho squared. What in opposite? In opposite, beta will be real, and we will see simple decay. Okay, 1 second. So EF, if less, will be minus E0 omega F, F power is alpha, right? Sinus omega Ft. U E, teiksim, will be omega 0 divided by omega F, E0, F power of sinus omega Ft minus, you will see angle shift. Okay, one moment. I have a network here. Yes.
Yes.
I have a network. Pulse generator. It supplies to microsecond pulse at each 3 milliseconds. This pulse charges capacitor, coil, variable resistance. I took this voltage as a yellow signal to my scope. And this is what you see on the screen.
Frequency. Signal.
Signal.
Kilohertz.
Let's make it more visible. Decade. You see? Wait. Okay. It's a sine function.
This is free current flow.
Yeah, it is free voltage.
Free voltage.
It's a voltage of capacitor. Decay. See, do you see exponential decay? This borderline is an exponent. So the signal is sine decaying by the exponent. Alpha determines this decrement, it's decaying, and omega F is an oscillation frequency.
Yeah.
We can change wait 1 moment, I will switch second camera. So, on one,
depending on alpha and oscillation, we do understand it deeply.
yes, one, everything will go. So, I'm changing capacitance. See what happens? The less capacitance, the higher is frequency. And also, you see time. Decay, constant of decay do not change. But time of decay, time till 0 changes. Why? Because amount of energy contour. It's an oscillation contour. Receive on each pulse changes. Capacitor needs to, I would say, take in this amount of energy. This is ferrite. Material with very good magnetic conductivity. What will happen? If I place this block in proximity of my coil? Physics. This is ferrite block, material with good magnetic conductivity. If I place it in proximity of my coil, what will happen?
We're going to change the signal.
What happens with frequency?
We're going to change it.
Which way?
I think upwards.
Wrong. If I increase magnetic conductivity of environment, this means that coil can accumulate more energy. More energy means more inertia, higher inertia. Higher inertia, lower frequency. If I increase magnetic conductivity, I increase, energy capacitance of my coil. This means higher inertia and lower frequency. Yes. And now, interesting moment. Active resistance. What happens? Let me change scale. Like this. If I change, I increase resistance. This means increase in decay. Here is critical point where active resistance is equal to the double wave resistance. If I increase more, see what happens. Process no longer oscillates. No, it's not. But now it's not a periodic process, but aperiodic. Rules of actuation are real. Imaginary rules.
Yeah.
Oscillation.
Decaying all
Real rules are periodic.
How was the situation in the beginning of the class? We had a different displaying on the board, but it was a different signal. Like you were on then off.
The same, but with different time scale.
So when we have a loop, this is how it looks.
Yeah, that's what inside. I can.
Oh.
Only time I change time scale to make it more. Oh.
Okay. Got it. So this, all of of them have the same signal. Everything is
Yeah,
the same.
that's what happened. I supply energy to this oscillation contour every. Where's my liquid adjustment? Every 3 milliseconds. 1, 2, 3. Next. 1, 2, 3. It's like hitting with hammer.
But this
It's
is,
small mallet.
yeah.
A small mallet, and I'm hitting. And I see decay. Here, what's inside?
Yeah. Okay. Oh.
Inside is decaying. I'm changing capacitance in this scale, inductance, and increase of resistance. Periodic, non-periodic. And now one thing. Do not see in both. My scope can perform discrete time Fourier transform on this signal.
Are we gonna work on the discrete math of signals?
Yes. We already we showed the discrete time Fourier transform, but I will try to work around to how to say. I would like not to overload course with this heavy discrete mass. I will try to work it around to make it simple. But yes, prepare. Yes. Red line is a result of Fourier transform. Of yellow signal. What do we see? All energy concentrates on one frequency. If I increase resistance, wider.
It's equalizing in the beginning.
We have the same amount of energy. Generator supplies same pulse. But what do we see? Oscillating. All energy concentrates on one frequency. A periodic. And we have large tail, multiple. I can make it more. It is it's a little help. Something like spectrum of periodic pulse sequence. Oops, where are you? And here, a bit strange.
Why it's not constant?
Because Scope calculates. It's a limitation of scope. See,
For theoretical results, do we take the average?
no, no. In theory, we should see one line. But here is limitation of scope itself. I will speak on Fourier transform limitations, on discrete time Fourier transform limitation. I will explain this effect.
Okay.
It's a limitation of discrete time operation. Try to help a bit my school. It don't like not any frequency is transformed in same way.
Yeah.
So what do we see? Decaying. If I put a borderline, it will be E0 divided by omega 0 L. A power is alpha t. Alpha, this line.
Yeah.
With small decays, free oscillation frequency is very near to the theoretical resonance frequency. For such oscillation contact, one characteristic is important. It's a decrement. F divided by rho, or F divided by square root of LC. Also can be written as, F divided by omega 0 L, or F omega 0 C. It's a characteristic of energy loss in contact.
So depending on alpha,
It depends on loss. Usually, quality of contour 1 divided by decrement is used. It's characterized quality. Actually, it's double P multiplied by energy ratio, where on the one side capacitor's energy, on the other side energy dissipation in active resistance. In good quality contacts, resistance is relatively small, so free frequency being omega 0 square root 1 minus L divided by double Rho square can be approximately substitute with omega 0 1 minus R squared divided by 8 Rho squared. Well, it's approximately omega 0. Oh, in case of low resistance,
Yeah.
now we can take a look on oscillation contacts. We can, what can we do? We can split in two ideal cases. One ideal case, we have kind of the AC source with the frequency in max cosine omega time. We have ideal source, coil, resistance, capacitance. And some current here. Maybe this is ground, A, points A and B. All in series connection. Series connection. In case of series connection, input resistance of, let's say, impedance, input is AB, it will be R plus J XC equals to R plus J omega L minus 1 divided by omega C. Point of resonance corresponds to imaginary part of ZAB or input resistance being 0. It's a point, so electrotechnics basically call it voltage resonance, or resonance of voltages. Moment where input resistance become pure actives or imaginary part of input resistance, what we will get? When at a frequency equal to omega 0 of 1 divided by square root of LC. Frequency of voltage resonance equals to omega 0. And what about voltages? Current at omega equals to omega 0. What we will see?
Omega equals to omega
A
0.
divided by A. When frequency is equal to resonance frequency, we will see max of current, E divided by R. Yeah?
Yeah.
And what about voltages? Increase of voltages. So UN will be equal, at a resonance point, UN equals to C and equals to E rho divided by R or Q E. Voltage will be Q times higher. Q is a quality of contour. For ordinary coil capacitor, it may be 20, 30. For high end, 300, 400. Significant. You need to be correct in your analysis. Equivalent quality of sequential contour contains resistance plus internal resistance of your generator plus rho square divided by L rho R. If you put some load in contour, it will decrease your quality. Analysis in in areas near, in proximity of resonant point, better to use voltage, sorry, not voltage, but frequency shifts. Frequency shift from the point of resonance. To analyze characteristic, frequency shift or frequency deviation used in relative form. Relative form of equals to omega square minus omega C square divided by omega square. Relative frequency shift and so-called normalized or overall frequency shift. Omega 0 and by omega. This is often used to, to compare. When we speak on bandpass filters, we need to compare different designs. This common normalized frequency deviation allows to create characteristic chart for different design in the same coordinate system. To analyze a peak of characteristic near the point of resonance. So if we are in proximity of resonant point, we are analyzing sphere of this, tip of this characteristic, sphere, tip of the sphere. Input reactance will be double rho, delta omega divided by omega 0 or rho epsilon Z AB input impedance R square root 1 plus C square, or approximately for analyze, use it for approximately analyze decrement square plus epsilon square. This allows you to create resonance chart. Simplified characteristic, assuming R is 0, it's a simplified characteristic. Current divided by current at the point omega 0, 1 divided by square root 1 plus C square, approximately can be drawn as 1 divided by square root 1 plus double Q delta omega divided by omega 0 square. Yes. Real, you will get characteristic like this. If you use such contour as a bandpass filter, you will get something like this with the point of omega 0. Transfer ratio. If you voltage from capacitor its capacitor voltage towards EMF, you will get something like Q omega 0 divided by omega square root 1 plus square. If you take coil voltage, you will get absolutely the same. It's equals to at a point of resonance. They are equal. At the point omega equals to omega 0, both Ka equals to Ka C and equals to quality. Version 1. What about model 2? I have 10 minutes, I'll start. Version 2 is you have source grounded with the internal resistance and capacitor, coil, case point A, R1, R2, this is point B, ground. Coil current, capacitor current, and contour, okay, it will be contour current.
So this is a different model.
Yeah, it's a model for parallel resonance or resonance of currents.
So you'll have a different signal on decay.
Different and not different.
Oh. So you'll have two different loops.
Yes, I have two branches. Let's say. At one, I have coil current, and other I have capacitor current. Interesting moment. There is one moment when imaginary part of 1 divided ZAB is 0. When imaginary part of conductance is 0. When reactive current of coil fully compensates reactive current of capacitor. At this moment, I can say that contour current, which flows through reactive elements, a contour being all AB divided by I can write it. Contour resistance is R1 plus dot omega A multiplied by R2 plus 1 divided by dot omega C divided by...
Is this not impedance?
Yes, it's impedance of contour. Not input, but as impedance of the contour loop.
Yeah.
R1 plus R2 plus dot omega L minus 1 divided by by omega C, sorry. Omega C. At a point of resonance, when frequency is omega 0, at a point of resonance, it will become pure active. They capacitor and core compensate each other. So it will be rho squared divided by resistance, or QR. It's a sum, R is R1 plus R2.
Give me a quality.
Yeah. Good, with the good quality. In theory, if there would be no losses, it would become...
But there's always going to be losses.
Yes, but in theory, if no losses, it will be infinity.
Yeah.
In reality, if Q, for example, 300, you will get input resistance in many thousand ohms. It will be quite high.
Can we have like multiple capacitors instead of resistors? Is a different model?
Nothing changed. We can have, wait 1 second, we can have sequence of contours.
Yeah.
We can have couplet system of multiple contours. I will get it. First I'm speaking on very simple thing, one contour. But we can have multiple contours. Analyze around or in proximity of resonant point of resonance. Contour current is QI quite high. It's much higher than a current taken or drawn from generator. In case we have small small frequency shifts, input impedance AB or input impedance will be rho squared divided by L1 plus it's E equals ZAB. Its value can be approximately impedance at omega equals to omega 0 divided by square root 1 plus C squared. Resonance chart of good contour. divided by O at the point where omega equals to omega 0 looks like 1 divided by 1 plus C squared, or approximately 1 divided by square root 1 plus double Q delta omega divided by omega 0 squared. It's when you create a bandpass filter, you can use this to draw a chart. Transfer factors. It's EA will be approximately Q omega 0 divided by omega square root 1 plus C squared for capacitor. It will be Q omega divided by omega 0. Here omega 0 omega, for capacitor omega omega 0 square root 1 plus C squared. At a point of resonance, these factors are equal to contour quality. Is the difference? First model works better when we have source with small internal resistance. This model works better when we have source with high output resistance. Equal quality is wave resistance divided by R1 plus R2 plus rho squared divided by internal resistance. We can try. I can try to do what? I can try to power this contour from the outer source. Only omega 0 here, 55, 56 kilohertz, something like this. Just to show how it is. Source. This will be S1. And this will be S2. I need this small capacitor. It will increase internal resistance of generator because naturally it's only 600 ohms. 1 nanofarad. Not okay. This is my ground. This is my ground. With such setup. Go here. Come here. I forgot to connect. Not a disaster. Disaster. Okay, I don't need you. I need to get okay. Can I have 1 volt? Oh, 1 volt. Input signal 1 volt. Output. I need measures. I have frequency, and what about for channel 2? I would like to have this one. Yeah! Here is my schematics. Resistance nearly 0. Decreasing frequency.
Yeah.
See, output goes down. Increasing frequency.
What goes
Down.
They'll have to be same or what?
No, they
Parallel.
should not be the same.
I think they should have.
Это point of resonance. Small problem. Where is my? Yes, it's correct. Division factor is too high.
Oof. Damn. This clipping post negative.
Yeah, its scope is unhappy. Scope is unhappy. Okay, this point is this is good. Point. Now frequency. I'm changing frequency. Whoop. Whoop.
Okay.
Here is point of resonance. I have 1 volt at input and 11.6 an output. I can maybe get a bit better result. One. Here. 20 volts from 1 volt. I will get camera on measurements. Here. 20 volts from 1 volt. This means quality on different frequency. Whoop. Here is point of resonance. contour resistance is pure active, and I see increase in voltage 20 times, so quality is 20. It's a resonant. Oops. So in frequency it will be something like this. I can change, okay? Change of capacitance. I decrease capacitance, and what will happen with resonant frequency?
Oh.
Oh.
Oh,
Frequency increased.
yeah.
Higher capacity. Oh. Lower resonance frequency. Same with the coil.
Yeah.
And what about resistance? Oh,
As expected, frequency lowered.
not frequency, but quality. I
Yeah.
increase losses in contact, and magnitude of voltage decrease instantly. Even small resistance, 10 ohm, 20, 30. See how it downgrades contour characteristic. No effect. Yeah. Here we have single contour. Do we need to take a break?
It's totally up to you, sir. I'm good. Yeah.
I think maybe split it in two parts or no?
But
What about this is single contour. Now what about couplet systems? Okay.
If that's a long subject, we can maybe split the subject.
Not very long. It's not dramatic. I only need to assemble another schematics. I'll need to assemble another schematics. Two.
So we have two more schematics, then that's it.
Double circuit. Here, at this moment, we have one contour. Now it's time to get two. Time to get two. Okay. I will assemble schematics. We'll see something. Or not. It will take 10 minutes. Expecting.
Are you still recording? Are you still?
Yeah. No.
You're not?
No. No reason to interrupt.
So can I just smoke a cigarette and come back?
Easy, yeah. I said it will take some 10 minutes while I assemble schematics. I will wait for you.
Do you need assistance?
No. I need to remember what I need to assemble. Oh, who's here? Capacitor. I want cowboy. System of cowboy contours.
Can you suggest some advices for us? For thesis?
For
We made for donor, but
yeah, but nothing and nothing productive.
I mean,
He's not
in the
available.
on days. Only Tuesdays we think he's available today, but the door is locked.
Promised me. Actually, I heard from him, but you ignoring, missing, and so on. Yeah, he complained.
We met him last week. Oh, mate, this one is pretty. Mate, college class.
Who is this?
We met him last week
Yeah.
and talked about the thesis.
And what happened?
And when we come today, he's not there.
You met?
Last week.
Last week.
Yeah, and met? This mean you talked with him?
Yeah.
And sent answer, but no, I will not help you, or what? What happened?
No, he said he will help, but how we can contact him? No ways. He's not replying to
Yeah,
email.
Yeah. How can we catch
Yeah.
our victim? Not replying, not communicating. Problem we have. what I want to hear. What can I say? I need to talk with him.
Okay.
What's going on?
Okay.
I can answer. What happened? What happened when you communicated first time? Agreed to work with this thesis? Or what?
Magnetic. We have topics similar to electrical vehicle stations, something. But his topic is related to magnetic field.
Yeah.
So, is there any process taking this type of grid, DC grid or electrical vehicle stations, something?
Once more. We have magnetical circuit of, say, traction machines or something like this. This I understood. And what I do not understand.
Orgono's research is in magnetic.
Yeah, in the calculus of magnetic circuit
Yeah.
and electrical machines.
I have the paper in. Wait. Fault in electrical charging stations, similar to.
Fault in stations.
Yeah.
On DC side or on which side? Or simple fault, spherical fault somewhere. On which side faults are?
Means the supply fault. If there is no supply due to some.
If there is no supply,
Yeah, we will back up with.
with what? With local generator
Yeah.
or taking power from electrical vesicles.
Something like that. I need to research.
Who sent you to this? Clearly, you're researching supply of local network from electrical vesicles, or you research supply of electrical vesicles from backup generator. Can we clarify?
Supplying the power supply to the electrical station.
From backup generator.
Yeah, generator, I think.
And generator? What kind of generator? Hmm?
Just a moment.
What kind of generator they are? What kind of generator they are dealing with? So it's not. Wait, 1 second. This is ground. No. What a mess.
ഞാനിവിടെ അപ്പൊ തന്നെ ആലോചിച്ചാണ് അല്ല പാടൊന്നും കണ്ടിട്ട്
ഇയാളെ എങ്ങനെ വിവരിക്കാൻ നമ്മൾ കാണിച്ചു കൊടുക്കും എന്ത് ചെയ്യാ നോക്കി എനിക്കൊന്ന് പറഞ്ഞേരെ
നീ ഇതിന്റെ ഒരു വോയിസ് കൂടി അയച്ചേക്കുന്നു പറഞ്ഞില്ലേ
അതപ്പോ അയക്കപ്പെട്ടെ This is a circle diagram for the you understand from
AB battery pack, system, and this is backup battery, and with cap of injection transformer. Understood, from local.
yeah.
So you're getting power from local battery.
From distribution grid.
How it will work? You will have a backup battery with backup inverter. And this backup inverter will I'm thinking who can help us with this problem. You need to research on backup system. He knows where the dog is digging. I knew who can help you. Пробуем вот. It's a problem.
Да.
ഇതാണ് ആ സാധനത്തിന്റെ പറ്റി അയാൾ എന്നെ പഠിപ്പിക്കുന്ന രീതിയിലാണ് ഞാൻ എടുത്തത് കേട്ടോ.
Пробуем вот. About this case.
ഞാൻ
You need to talk real bro in this is Ilya Gauken professor. But if you have problem hunting Podgornov, you'll have 3 times serious problem hunting Professor Gauken. You'll be problem. Maybe online people can tell us what to do with backup inverters. Nope, no one. They're sleeping at their computers. They are sleeping. Try to read. No, our building administrator. Alexander, our building administrator. Ask him when I can find Ilya Gaukin, Professor Gaukin. For in your problem, best one here is Gaukin. But hunting him, sometimes he drinks coffee at the administrator, near the administrative desk.
Okay.
He loves this coffee machine. Gaukins. Yeah, Ilya. I need Ilya. But
in Outlook.
come. Have schematics ready. Go. Professor.
You guys will see.
Can you show in Outlook?
1 second. You. Oh. Ilya Gaukins. Oh, look. Ilya Gaukins. Maybe some. Oh, here. Yeah. Ilya Gauk is a. But hunting him is challenging.
Okay.
The one who really can consult you on this matter. It's his point of research. Okay, I need to go back to resonance circuits.
Sir, can you look?
You look there. they will. Who gave you this? Oh my God. Ah, control of DC grids. Directional converter model. Who's digging well and who they can torture? You know, the student in your group, hi Sergey, this tall guy. Remember?
Erasmus.
Yeah. No, he's not Erasmus. He's local. It's Sergey.
That pattern.
It's his thematic of the poem.
Okay.
Okay, I need to.
Okay. Student? He's a
Yeah, student. He's writing diploma on this.
diploma.
It's thematic of his diploma.
Okay, thank you, sir.
Thank you, sir.
Welcome. What's here? Oh, I have network. It's very suspicious network.
Looks like flipping upside down.
It's a suspicious network. I don't think.
Looks like DNA.
I don't think you saw something like this previously. Suspicious network. Okay, now in first in previous hour, what we deal with single resonant control. Now I would like to take a look on couplet systems. So I have two resonant systems with some kind of coupling between them. So energy can travel from system 1 to system 2. Here, pair of condensers and mutual couplet coil between them. There is idea of coupling factor or coupling ratio. Sorry, this is no Latvian side. Side means connection, link, something like this. So this is situs coefficients in Latvian. In English it's coupling factor or coupling ratio. S from Latvian site, link, connection, junction, something like this. It is square root K12, K21. So I have system 1, system 2, K12, K21. One, two, two, one. Radius of voltage transfer between systems. I have some kind of coupling between systems. So voltage rating. For example, I'll try to explain on example what's this. So I have N R1, L1, C1, L2, R2, R2, C2. Two contacts coupled magnetically. Here I1, I2. What? Do you know what magnetic coupling is? What's the meaning of this symbol?
No.
What's the meaning of this symbol? Can you phone tell us?
Magnet.
No, I want to hear.
Like magnetic coupling, like transferring voltage from one coil to
Yeah.
another.
When two coils have common magnetic flux. Yeah. In such case, what's the measurement unit of magnetic coupling? As inductance, Henry. What means 1 Henry in magnetic coupling? If you increase current in primary system to 1 unit, for example 1 ohm, voltage induced here will increase 1 unit, 1 volt. Its amount of volts induced in secondary systems per ampere in primary system. Measurable in henries. In such system, 2-1 will be by L2, K12 will be, wait 1 second, 2-1, 1-2. Yeah. And coupling factor is divided by square root L1, L2. L, self-inductance, and M, mu to R. This M is from motor. Another way to couple to system is so-called auto transformer. Coil. Nice coil, but it has taps, so-called taps. It has attachments in the middle. 1 second, I wrote it somewhere. Where I wrote it? It had, on the coil itself, overall inductance 1 millihenry, and why not? Strange. I forgot to write where the tap is taken. This has overall inductance 9.68 millihenry and tap 1 free. Tap 1 for 268. Coil with taps. In this case, we will deal with L1, kind of L0, source, L1 capacitance. Oops. L. So L2, R2 and C2. Oh, system of coupled contours with a so-called autotransformer using a tap from the coil. Should be here. Some scrolls to have coils with many taps. Special coupling coils where needed tap can be selected with the help of switch. For such system, such system K21 equals to Ls L1 plus L0 K12 equals to Ls divided by L2 plus L0. Stop. Yes, sorry. And our coupling factor is L divided by square root L1 plus L0 multiplied by L0, Ls. Yeah. Also, one of the quite popular thing is a coupling with capacitors. There is two versions with internal capacitor, so-called internal capacitor, and external. 1 second, I will draw L1, C1, L1, C. This is coupling capacitor. In this version is so-called internal. C2, R2. Version with internal coupling capacitor. Here, 2,1 equals to C1 divided C1 plus coupling. K12 equals to C2 divided plus CS. And common coupling factor between systems. Equals to square root C1, C2 divided by C1 plus CS multiplied by C2 plus CS on. This is version with internal capacitor. Also, I can show you artifact from past F1. Once here in Riga we had developed radio industry. Our state electrotechnical factory produced this. In its day it was the desired receiver because it had very good receiving characteristic. And key element in this characteristic, see this aluminium like boxes, set of them. The inside are coils and near them brown is 1, 2, 3, and near them brown and gray capacitors. These receivers to achieve good selectivity use so-called concentrated selectivity filters created like this. It's a chain of resonant contact with external capacitive coupling. Very good for long range receivers, for DX receivers. R1 L1 C1 coupling capacitor C2 R2 L2 here ground containers. Should be somewhere in 70s. Oh. 79. This one, 979. In its time it was a good receiver. Relatively. How to say, good civilian receiver, not pro. Okay, for external, 2,1 equals to CS divided by C2 plus CS K1 2 equals to CS divided by C1 plus CS, and coupling ratio will be CS divided by square root, here should be C1 CS multiplied C2 CS. Couplings. All these schematics I can, how to say, I can set a common network for them. For all this type of schematics, I can reduce, how to say, my analyze to the network like this. Second side impedance, primary side impedance, and coupling impedance. The ground A. For simplicity, Z11, Z1, Z22, it's a self. Input impedance of this system, ZAB, or input impedance of this system will be 1 plus ZS Z2 divided Z2. So input impedance or ZAB can be written as self-impedance of the primary system minus square of coupling impedance divided by self of secondary system. This part, negative, is so-called transferred or introduced impedance. It's an influence of the secondary side into primary. Usually, we can assume a real part of ZS 0. And this introduced or what I'm doing. We have this introduced on transformed part. So this transformed or introduced part being square divided by we have its active part. x coupling square divided by square of secondary resistance magnitude, this thing reflects losses on the secondary side. And primary, what primary? X in minus square divided by square is an introduced reactance. This thing changed frequency of the resonance. I have one network. What kind of network do I have here? 1 second. I'll do a schematic. I have pulse generator. It produces pulses to microseconds, and time between pulses should be somewhere around 3 milliseconds. Oh, now it's exactly 3 milliseconds. 3 milliseconds. It's a diode. It powers. What it powers? C1. This is C1. L1. Adjustable C2, L2. With adjustable coupling. You spend some time on that. You see such systems first time in your life, and I'm afraid last one. No one wastes the time on this. I'm afraid I'm the only owner in whole region of this thing. It's adjustable mutual inductance. What I'm changing? Coupling between systems. Yellow line here. S1. Blue line. Look, I'm disconnecting secondary side capacitor.
Disconnecting?
Yeah. Maybe stronger. See change in frequency. Because when I disconnect secondary side capacitor, there is no current on secondary side. But introduced part of reactance got disappeared. Now, what do we see?
frequency is getting concentrated for the parts that are weak in the opposite.
Small coupling,
Yeah.
relative, higher, higher, higher. Oops. Here is very small coupling. We only see,
I think we have seen something similar to this.
we have
at the
two
previous-
resonant contacts with small coupling between them, adjusted to same resonant frequency. Here, metal coupling is near zero. Here it is near zero. I increase coupling. And what? In bit high. See what happens? Secondary side starts pulling energy from primary.
Ah,
See decays faster.
yeah. What if you give the max of energy potential? So I think the energy becomes larger than the primary section.
And
the second.
yeah, you see magnitude higher.
Yeah.
It depends on resistance. But what's this? Higher coupling, part of energy goes from primary side to secondary. And at some point, you see the strange change. In opposite side, there is one moment, series, when we try to determine resonance frequency, at which frequency this network oscillates. We can analyze input impedance of this network. If we deal in near, now they are operating at resonance frequency. I adjusted them to resonate at same frequency. In case of small differences, we can approximately say what and are equal to rho epsilon. It's approximately, we can do it only at near resonance frequency. Coupling impedance will be rho coupling factor. We can approximately substitute magnitude of secondary system impedance with rho square decrement square plus square of frequency shift. And we will see two resonance conditions. Actually, resonance condition of whole system splits in two. One is zero. This means frequency equals to resonance frequency of primary side. No, they all. I started adjusting them to same frequency.
Yeah.
And second one equals plus minus square root Ks square minus square of decrement. It appears what I will have two resonance frequencies. For this case, I have one only resonance frequency. For this case, I will have two. And it's depending on strength of coupling. Really, I will see two resonance frequencies. Omega 0 divided by square root 1 plus square root coupling factor square minus square of decrement. And second frequency being omega 0 divided by 1 minus square root minus decrement square. Fourier transform. Channel 1. 1 second. I will. Oops.
What if we have an imaginary number result at the denominator?
We can have imaginary here. Look what we have. Look at red line.
Yeah. Same one.
Single frequency.
Yeah.
I'm increasing coupling.
It got waved. Because we have two sections now. That's why.
No, because we got this in small coupling.
We only have one.
First condition works. Now it complies with the first condition.
Yeah.
I have only one resonant frequency.
Yeah.
With increased coupling, start playing second condition.
We have only
Can you see that line? Maybe I will shift here and here. Small coupling, relative. One resonance frequency. One. Stronger coupling. And signal contains two frequencies. It can oscillate on any system, can oscillate on any of these frequencies. Two. Simple capacitor discharge or coil energizing. System with degree of 1. Single resonance contour. System with degree of 2. Has two roots. They are conjugate. This is system of fourth order. System of couplet. Resonance contours has two. You see?
But do we prioritize the other small waves at the bottom? In the red line we have
But
like,
these
yeah, they're small, but we have
they are small. At this moment we see there are no waves. When I speak on limitations of discrete Fourier transform, I will explain what are these waves, why they appear. These are not from signal, these are from transform itself. It's a limitation of digital signal processing.
Oh.
In case of ideal transformation, there should be two vertical lines.
Yeah.
But we don't get ideal vertical line because scope has a limited memory and limited sampling time. I will explain it. It's a limitation of scope. Now I need the closer coils, the higher is coupling, the highest influence between primary and secondary side. See the distance? This one grows
Yeah.
and frequencies are wider. One second, for small coupling, we're getting something like this. For higher coupling, something like this. One second, I will write transfer formula. For this one, transfer factor as a function of frequency, only its magnitude. So it's secondary voltage, voltage divided by energizing epsilon will be something like coupling factor divided by epsilon 4 plus double epsilon square d square minus square plus d square plus ks square. Here is transfer ratio for area near resonance with small difference. Usually such systems are adjusted. In case you have different frequencies, let's say you have resonance frequency for primary system isolated with disconnected serial omega 1 and for secondary omega 2. These are resonance frequencies. Maybe use for primary and secondary side when other side is disconnected. In such case, peaks of characteristics, you will get characteristic like this. This is omega 1 and this is omega 2. In case of different frequencies, something like this. I changed the frequency of secondary part. So, in case of different frequencies, omega 1, 2 will be square root omega resonance 1 square plus omega resonance 2 square plus minus square root of omega resonance 1 square plus omega resonance 2 square square minus square root continuous minus 4 omega 1 omega 2 1 minus coupling factor square upper root ends here, and that's not all. This should be divided by 1 minus third square. Division in red. Here is formula for two frequencies. I would like to make this more visible. Two frequencies. The wave you see, it's actually a difference. If you draw a line like this, frequency of this line will be this difference. I would like to employ one instrument. It's called analyzer of amplitude frequency characteristics or body analyzer. Idea: take a generator of such voltage, use it to control by frequency generator of harmonic signal. So it will wobble. It's called wobbler. Frequency will go up and down, go up and down. Apply this, okay, you will need proper amplifier. Apply this to your test network. Again, amplify. Absolute value. Now, so this will be Sx and Sy. Take a CRT. Use wobbler control signal as an X signal for CRT. And apply this to Y channel. CRT will draw a research figure. Yeah? What will be coordinates of this figure? Good to have also AGC circuit, automatic gain control circuit, to stabilize voltage. So what will be? On CRT, we will have research figure with coordinates, frequency, magnitude of transfer function. Understand why? AGC ensures what here we have constant voltage. So, output from the circuit as a function of frequency.
This looks like a tank.
This looks like an old, good analyzer of frequency characteristics.
How much is this if I want to buy this?
You will look for them because contains rare earth and gold and silver, and it's a military model. You will spend 400-600, maybe more.
4,600.
Yeah, it's a rare thing. Actually, it's older than me. You can find newer model are less expensive.
A few minutes ago you said that I am the only owner maybe
Yeah,
about
here in the
that
region.
device.
Yeah, this called carbon
Is
coil.
it that expensive or rare to find?
Rare. They only appear on British market. I hunt them in Britain through eBay. They were all these manufactured. This coil is 50s and capacitors 1970, 1980, something like this. Left one for aviation ministry, and it bears King's property mark. Right one, I'm not sure. Maybe civilian, maybe military. Appear.
Looks like military.
Maybe, but no marks. And no manufacturer mark. It should be Marconi, but this one don't bear the manufacturer mark. Left one Marconi. It should be Marconi. What I need? I'll need a circuit. 1 second, I will get my test. Number 1, simple resonance circuit. 1, very good quality coil. 1 capacitor, and I also have resistance here. Test signal, come here. And this one is for input. Always problem with them. Come on. Please. Always problem. Where is? Oh. They are not so bright. Can you see characteristic?
Yeah. It's like a circlish thing, but
Looks like a heel.
yeah. To the other side.
This one, this one. Okay, come on. I will Oh, maybe a bit higher. Oh, here it is. Characteristics of this is my resonance circuit. What I can do, I can change capacity. To get some space for my hands. Here we are. I'm changing capacity. If I increase capacity, where characteristic goes? Phone addicts. Where characteristic shifts when I increase capacity? If this is resonance, this is resonance characteristic. If capacity increased, where it goes? To the right or to the left? It's a chart as a function of frequency.
If capacity increases,
Yeah,
where does it go? Left or
yeah, left or right? Where will it go?
I have 50% chance.
Yeah,
Saying right.
you don't need more chance. Capacity increase, system inertia increases. System inertia increases, frequency decreases. Frequency decreases, it goes this way,
To your right, to my left,
this way,
it's left.
to the origin of coordinates. Watch. The capacity decreases, goes this way.
Yeah.
Capacity increases this way. I don't know, right or left, depends on. And why magnitude change? Do you see what magnitude change?
Yeah.
Why?
Because of the capacity.
Amount of conductive material. When I change capacitance, I change active area of veins. The higher is active area, the more veins are, I would say, in business, the higher are active losses because current flows through veins.
Yeah. Obviously.
Yeah, obviously, for me. High capacity, low quality, because losses increase. Low capacity, see, higher magnitude, because losses are less. Okay, let's, for example, take this. Now question, this is ferrite. Material with good magnetic conductivity. What will happen with frequency when I put it in coil? Magnetic conductance increases. Amount of energy stored increases. Inertia increases. Frequency goes down because of high inertia. Watch.
Yeah.
And also, you can see how losses increase. Because magnetic material, maybe like this, then now, Next experiment. Aluminium. It's a piece of pipe. What will happen?
It has no conductivity.
It has, why? It has active yeah, it has no magnetic, but it's electrical.
It doesn't go to the left side of the origin.
Yeah.
And it moves to the right.
It goes towards increase. Frequent. If I put magnetic material, inertia increases,
Yeah.
frequency decreases. If I put diamagnetic, it decreases magnetic energy because current circulates in conductive. So frequency increases. Okay, this was system of one coil, one capacitor. And we see its resonance. Oh, BTV. What happens if I introduce resistance? See, I decrease quality. And characteristic goes down.
Can you measure some exact values over there?
Yes. It allows I can change the incremental scale and I have a frequency. I can also, 1 second. You see green ticks?
Yeah.
Each tick is a 10 megahertz. If I please. What went wrong? Ah, sorry. If I switch this one, each tick is a 1 megahertz. So you can draw characteristic in megahertz. These green ticks now are 1 megahertz. What I need another object. 1 second, object will appear. My object, it's a pair of resonant contacts. This one, wait. They should be adjusted to 1 frequency. They were adjusted same as before. Okay. Here they are. Small coupling. Higher coupling. You see? 1 peak in resonance. Closer. And wow. It's doubles. Maybe. on small couplings, we have single resonance frequency. High coupling. Come on. And it galbus. Brighter. Maybe. Oops. Small coupling, single frequency. Close coupling, double, and we have double. In a case of very good system of very well coupled coils. They sit on common magnetic conductor. It's a core of magnetic conductor. It's kind of ferrite. It's magnetic material. Oh, yeah. Sorry. Here, you can see characteristic of very well coupled in different scale. My finger. I introduce losses with my finger. Where am I? So here is characteristic of very well coupled system. Two frequencies, and that it can resonate on any of these frequencies. Fourth order system. this. Magnetic coupling. I need. Let's see, will it work? It works. What's so interesting? How many such things you saw in your life? Zero. In real life. Yeah? How many? Not on TikTok, but in reality. Life. Zero. Why are you here? Can you answer me? Blah. How it works?
You're generating energy while
Yes, I'm generating DC.
spinning the
Oops.
armbar.
Camera hates me. what happens?
The armature is rotating, so
It produces DC 1000 volts.
there is a induced EMF.
Capacitor. This capacitor charges. Take this off. Until this gap breaks. At moment it breaks, capacitor discharges through coil. And on primary side, we have decay oscillation, like this one. Coils, this large and this, this primary coil and the secondary are coupled. Oscillations in primary induce current and oscillations in secondary with high amplitude. They are resonance tuned.
What about two metal balls?
Metal balls are forming capacity, and I need to discharge it. I need this capacity. It's created with this ring and this ball. Classical Tesla design. What's this? Famous Tesla tower. It is a Tesla coil in its original design with discharge gap.
In the old days, this Tesla coil was destroyed, like last year.
Tesla tower Tesla built is way there was destroyed, but I have my own pocket, how to say, not pocket but shelf version. It is in, how to say, in flash. Real. This resembles Tesla designs. Only Tesla later made kind of cupola here. I can use separate both. It's also a system of coupled resonance contacts.
Pulses?
Yeah, this is it. Tesla transformer is clear example. It's the same thing with my demo. Two coupled resonance. Nice toy. Okay, I see. What? Time is out.
We have 15 more minutes.
In theory.
Yeah. Are you gonna attend the other class? No. No. We do have, but nobody's around. Okay, you do that. I didn't sleep for the whole night. I better go sleep. Studying is too hard.
Come on. Don't think it. stay like this. It's not so impressive. Wait a second. I need better connection.
Россия.
If I switch TV off, it's not so bright. Inside are funny xenon discharges.
Ah, yeah. I can see it now. Mythical. Yeah.
Pocket lighting. Enough. Please, folks. No, it's not impressive. GE. Okay. I think it's enough for today. Maybe some questions, maybe.
For today?
For today, what am I doing here? And where is the escape route? Yeah, I understand. These were small formulas. Much heavier will come.
You seem happier about it.
Of course, I'm happy. And I'm paid for this. Okay, maybe online someone want to ask some question.
Are we gonna have a project to pass the course?
We actually, if you take a look on your learning system, there are tasks already published. To get positive marks, solve just one.
If I solve one, I pass the course.
Yeah.
Any of them.
So we should submit the like while writing this on the paper and
You will need. You can send it me as a Word document, as a PDF.
okay.
No, paper isn't mandatory.
No, when we are coming, we can like prepare that one and can we submit to you?
Can, yes. But first solve.
It sounds easy,
It sounds easy.
but it can't be easy to do.
It sounds easy.